Hello, I'm Dr. Ben Britton, and I'm going to be presenting this lecture series on Introduction to Focused Ion Beam Microscopy. The lecture course itself is about 7 parts, and it will include a range of topics. We'll see that in a moment. I'm now at the University of British Columbia, and I'd like to acknowledge contributions from a range of colleagues, both at UBC, Imperial College London, Oriel, and TESCAM. So this lecture series is sort of brought in part to support activities at UBC, which includes the characterization at UBC Research Excellence Cluster, where we draw together effectively 9 facilities across 2 campuses, and the goal of the cluster is to explore, develop, and enhance our opportunities to understand the materials in the world in 2 dimensions, 3 dimensions, and with in situ methods. The cluster itself focuses on X-ray, optical, and electron microscopy methods, and of course this focused ion beam course overlaps closely with the electron microscopy methods, as we'll see in a fair bit. To find out more, please visit characterization.ubc.ca. So for this lecture course, I'm going to do the first lecture in this series, which is Introduction to FIB, and give you an outline of some application areas where it's useful. So the talks themselves, well, there's broken down into 7 sections. This is the first section, Introduction to FIB and Applications. And then there are effectively 6 following lectures of varying lengths. We've got basics of focused ion beams, so that gives us some underpinning theory behind ion-matter interactions and a few other details. Then we go into milling and polishing, which looks at how do we mill and polish surfaces, an essential aspect of sort of the machining in particular parts. Then we've got deposition and actually etching using, say, gas injection systems to enhance our ability to protect surfaces, create 3-dimensional structures, and also remove material at faster rates. We can then apply these approaches to enable us to do lift-outs, both TEM lamella, atom probe tomography, and tomographic work for, say, X-ray and electron methods. Then we're going to apply analytical FIBSEM to do 3D tomography and analysis, and we're going to see how that works with some case studies and a full detail of sort of the how one experiment for a magnesium indent is performed. In lecture 7, there's some future directions. This includes things like looking at different ion sources, looking at alternatives to FIBSEMs and complementary systems such as tri-beam lasers, and also to support activities within the cluster. We extend to explore the current offerings at the University of British Columbia, so capabilities that we have. The goals of this lecture series are to provide what I hope is a fairly comprehensive overview of focused ion beam based microscopy. And this overview and introduction is there and has been created to enable people to get the most out of the instruments, to provide the hands-on training with underpinning theory and support, to help people get some background and upskill in these particular areas. There are a range of ways that different learners will be involved in using these lectures, I hope. This will involve watching them sort of through in one block, but also taking your time, scanning through the lecture notes, having a look at individual dipping into topics as needed, or perhaps refreshing on core topics as they progress. So this should supplement hands-on sessions, especially for our instruments at UBC. I'm really hoping that this will enable people to come better equipped to our training sessions. The lecture course is quite comprehensive, and so it provides quite a deeper dive into literature for core topics, and figures and ideas are referenced throughout, and so that provides people learning opportunities to move beyond the lectures themselves. This sort of background information is, I'm hoping that people have, perhaps a little bit of experience or plans for sort of this area. Certainly my background is in using a FIBSEM for sort of material science and engineering applications, both hands-on and within my research team and with my collaborators. We perform cross-sectional analysis, tomography, and machining of FIB mechanical test objects. We've done a fair few lift-outs of the varieties that I've already mentioned in there. And so that gives you a little bit of a background of where this course. The course itself will extend beyond that. It has some biological systems, some photonics, optoelectronics, and a few other application areas as well. So if we just look at the basics of what FIB enables us to do, we can of course use the ion beam as a method to form a signal and to create images. But perhaps more popular in many cases is the use of the instrument to do machining, and that machining can be a sort of additive form as demonstrated with this sort of nano wine glass or micro wine glass. But we can also do this as a whole range of other bits and pieces. We can cut holes and reconstruct surfaces. This is the so-called micro house, one of the smallest houses in the world that's been made. We can use this for device edits for electronic systems, and if we combine this with an electron microscope, we can have a so-called dual beam system, which is now the most popular type of FIB-SEM or FIB systems out there, and that enables us to use things like tomography for slice and view, but also combining this with other electron microscopy analytical methods, and we'll see examples with EBSD and EDS for structural analysis with electron backscatter diffraction, and chemical analysis with energy, X-ray, electron, X-ray, anyway, we'll remember what that is in a minute. And then we can also use this to sputter away the surface of materials, energy dispersive X-ray spectroscopy, apologies. Sputter away materials, and sputtering can be used. We can look at the sputter cloud through things like secondary ion mass spectroscopy. So let's just look at a few examples. So we've got some nice examples of imaging. If we have different grains and different structures, we can see that surface microstructure. Different grains give us different contrast due to crystallographic information, and we can see things like pores and topography as well. We can use this to look, this is a really nice example in an aluminum beverage can, and we can see inclusions, we can see grain structure, and we can see the surface packaging polymer label. We can also do grain-to-grain contrast and do an EBSD-like experiment. This is some really nice work from Cyril Langlois and colleagues. And in this example, they effectively rotate the sample through a series of different angles and produce the characteristic blocking pattern for individual grains. And then you can use that and look that up against the table to work out the crystallographic orientation, almost like EBSD in that practice. We can also use the FIB to etch and remove the material, because different grains and different structures get milled at different rates. And so this is a nice example of a sort of bainitic steel, where we can see prior austenite domains kicking around. We can see the sort of bainitic, almost like ferrite-like structures in here. And we can also see quite nicely precipitates that are decorated or shown quite clearly in this microstructure, when we've just milled it a little bit, and then either imaged it with the FIB or imaged it with an SEM following. We can do cross sections, so we can cut, slice through the object and then do a single view. This is in a tin bismuth alloy. This is actually just before a tomography experiment, and we can see beautifully that microstructure inside the surface of that material. This second example is looking at an optoelectronic device, and so here we can see a series of different layers, and we could do metrology to measure the number of layers or thickness. And here we actually demonstrate that the presence of a capping tungsten layer is very, very useful to enable us to cross-section this material nicely. Without that cap, we get a significant amount of surface damage for xenon cross-sectioning in this case. We can also do tomography experiments, and so here we do slice and view. This is a beautiful example, I hope it will show, where we have a steel sample, and effectively we've done a series of different slices. This is about 200 micrometers by 200 micrometers, and here we can see backscatter electron microscopy, and we see through the digital reconstruction how that microstructure varies in 3 dimensions. And that can be really useful to look for embedded particles, interfaces, or 3-dimensional morphology. The challenge really here, as we'll discuss a bit later, is in order to interrogate this data, you often want to label it well, and that can be done, for instance, through these days through things like machine learning to enhance the ability to automatically label microstructures. So in addition to slice and view backscatter electron microscopy, we can also do slice and view EBSD. So at every single point we've collected an EBSD pattern, And so this example again is a steel sample where we can see the crystallographic orientations and microstructure, and we now have significantly improved contrast as well as descriptors of that microstructure. We can cluster these together to tell us the three-dimensional grain structure, and we can use the EBSC data to look at things like the interfacial plane normals and other such. We can also do energy dispersive X-ray spectroscopy at every single point, and here we have a tin bismuth system, and we can see beautifully through this 3D structure. This is almost like herringbone, as we call it, microstructure, and then we can see a decomposition of the eutectic that surrounds it. And this three-dimensional microstructure, this is with a xenon fib, is a relatively large volume, and this enables us to really get some very powerful chemical information about the microstructure that's presented in this material. We can also use this for biological systems, and if we do some clever slice and view, we can effectively have our objects that we protect with a platinum cap. We use the fib to remove each layer, we use SEM to image, and then we repeatedly remove it, similar to what I just showed you. But now with the biological systems, we can effectively have a target cell that's embedded inside a media, and then we can reconstruct the cellular morphology at the sort of micron to nanoscale. And so this again is a beautiful example from this review paper by Narayan and colleague. We can also do cryo-EM prep, so we can basically put the cells in a buffer solution. We can then plunge or vitreous freeze, and then that vitreous freeze enables us to have effectively amorphous ice, so we don't damage the cell itself. The sample is on an EM grid, and then we can use fib to either produce a wedge to look at the inside the material, or we can cut out a lamella to put this into a TEM and look at more detail to look at this sort of ultrastructure of that system. We can also use the FibSem as a sample preparation method, and so this is an example that we'll delve into a lot more detail later, where we've effectively gone and we've put a capping layer on top of a steel to produce ultimately a 5 micrometer cross section, where we can look at that microstructure with, say, TEM methods. So here we do the electron beam cap, ion beam cap. We've cut trenches around the region of interest. We've cleaned up those trenches to give us a beautiful, cleaned up the lamella. We've then rotated it to the top and we've done an undercut. You can see just about the undercut appearing in here. So the sample is now relatively free. It's called the J-cut part. And then we introduce a nano manipulator. We weld the manipulator onto the sample, and we free the cut off the sample, so the sample is only attached to the manipulator. We then lift the manipulator out of the sample and move the sample over to a grid, a support grid. We then weld the sample to the support grid, cut off the manipulator and move it out the way, and then we can thin the lamella to transparency, and that enables us to then use this big grid to move this sample to another instrument. And this enables us to do site-specific work from bulk samples, which is very useful. So here's a different TEM sample. This is from an aluminum alloy. We have a grain boundary and a series of precipitates. This is showing effectively quite nice high resolution analysis in this example. We can of course go to greater resolution in practice, but this gives a nice overview. We can do micromachining of mechanical test specimens. Here we have a compression pillar after it's been deformed, and we can see we can select out, say, single crystals or single precipitates. And here we've deformed the object with a controlled deformation, and we get actually 3 slip systems that are operating in this example. We can do site-specific lift-outs to enable us to do atom probe tomography. This example is shown in a lot more detail later, but this is really nice to do atom probe tomography to look at particular interfaces. And so in this work we were looking at the deuteride growth front, and we see this deuteride versus alpha zirconia matrix, and we can look at the decoration of zirconium and tin in this mix, and we found some really neat bits and pieces in there. We can also prepare samples for micro CT, and so this is a sort of a larger needle, but effectively we've got a capping layer, we've got the material of interest, and then we have a post that enables us to manipulate that sample and bring it to a synchrotron in this example. We can also use the fib to effectively mill labels. That can be quite useful to find out where samples are on our experiment for, say, in situ or other such experiments. But we can also put markers to enable us to do alignment, and this alignment was essential. In this case, we're actually going to do tomography afterwards to remove layer by layer of this object, and we use this fiducial marker to align the sample between slicings. We can do cross sections. This is of a solder ball, and we can see with effectively we've got beautiful microstructure that appears in the cross section without having significant damage. This is quite difficult to prepare using other methods. We can have a device system where we can edit that device by cutting or welding. We can effectively change the electronic path by cutting and breaking a circuit, but also making new layers with gas injection systems for deposition methods. And this is the example I showed you a moment ago. We can look at effectively tomography to do lift out and analysis of those objects if we so wish. Another area that we can use the fib for is we can do residual stress measurements. In these experiments, effectively, we cut a slot into our material, and as we cut the slot, if there is residual stress, the material will relax because the free surface has to have zero traction, and the strain that's measured can be measured effectively doing digital image correlation before and after the slots were cut. We can measure the magnitude of that strain and then relate that to the stress itself. Other areas is we can manipulate other objects, and so this example we're going to sharpen an atomic force microscope tip, and this enables us to greatly improve the resolution of the AFM, and this is a really nice example showing that improved metrology associated with a sharper AFM tip. This is with the sharp tip, this is with the tip before it was sharpened. And so ultimately, why does this work? Well, we're going to use charged ions, so we can use a series of different ions. We'll see a range of these, but we can have helium ion microscopes, we can have gallium liquid metal source fibs, and we can have xenon plasma sources. We're going to bring that focused beam, and in the process of effectively striking the surface of a sample, we can get sputtering where we eject the matrix material out to the side. We can also get the generation of secondary electrons from that process. And if we also use things like gas injection systems, we can get an interaction of the ion source with the gas. And that could be used with gas-assisted etching or selected deposition, depending on how we set up the instrument. We might also want to neutralize the charge, and so we can put effectively a charge neutralization system, and that can be quite useful. The incident ion can also cause damage to the lattice itself. In addition to creating holes and sputtering material, we can get implantation and other point defects and other things happen. This enables us to have this instrument to be beautifully powerful because we can do, of course, imaging with the direct probe, we can do sputtering, and we can use this as a sort of nano scalpel to cut up the material at the nano to micro scale quite nicely. And we can do analytical analysis of, say, the sputtered ions through things like SIMS in those systems. The overall instrument has that interaction happening at the sample, but basically what we do is we have the fib, it can be located off to one side. Some instruments may have the fib running vertical, but in many they'll be running off at an angle. We can have the fib with a series of ion electron optics in here to enable us to have the source that then brings it through some apertures, enables us to scan, and then we can focus. We have the fib hitting the sample coincident with the electron source hitting the sample, and that enables us to, for instance, image and target the location and then attack the sample with the fib. We can combine this with the analytics such as the secondary electron detector, the ETD and the SEM, but we can also add things like backscatter electron detectors and a few others, energy dispersive X-ray spectroscopy and electron backscatter diffraction. We can also have nano manipulators and gas injection systems that can assist in our operation of the instrument. The fib techniques, as I sort of shown or discussed briefly, we can do subtractive processing, where we sputter away materials to create three-dimensional structures. We can do defect engineering, where we can introduce disorder, vacancies, and impurities through the ion interactions with the matter. We can do imaging and tomography, where we basically use the subtractive processing and the electron beam to image afterwards. And then we can do digital reconstruction. It's kind of like reading a book, one page at a time. We can also do elemental analysis, where we've got the primary ions hitting the sample, and then we can have the secondary particles that then go through a mass spectrometer to work out what was being spotted. We can also do the manufacturing of objects through gas injection systems. So we have a precursor gas that we break down under the fib, and then that enables us to do almost, well, nano 3D printing in this case. And there's also a range of other processing modes that we can use the technique for. Now, one of the bits here is that fib can be quite challenging. There's plenty to use and plenty to think about, but successful fib use hopefully has a reasonable understanding of the ion column optics to perform a nice experiment. We're also going to optimize to, for instance, reduce damage where possible because we understand ion matter interactions. And we're also going to have an appreciation of why we might want to use a xenon fib or a gallium fib or other sources. When we're using this in anger, we'd like to know how to mill the material to manage cross sections and sputter yield, and that is also going to be linked to the understanding of deposition and etching, and specifically the role of the gas injection system. This will enable us to do things like lift out and tomographies, and we might want to appreciate the specific configurations of our local instruments. And this is effectively how this course is going to be echoed through the individual chapter sections a bit later. So hopefully I've highlighted that fib instruments are valuable for nanoscience. We can do a whole range of experiments and prepare samples, tomography, machining, etching, device edits, sample prep, and much more. And we'll typically use these in a materials-focused application, although materials is quite broad. These could be metals, alloys, ceramics, semiconductors, biomaterials, and many more. What I would suggest is that maximizing your ability to use fib effectively does require you to have a general awareness of the many ion matter interactions. In practice, you'll find that effectively it is a skills-based microscopy technique, and here effectively getting used to the instrument almost has an artisanal feel to this. But the artisan is best equipped when they understand how their tools are working as much as possible. So with that, I'm going to conclude the first lecture. The second lecture will go into how fib works and provide lots of the fundamentals. Please join me on the next YouTube lecture for this.